All right, hey there, class. This is lecture 2 on conversions and calculations, and this is a very important lecture. It's going to be something that you're going to see throughout the class, the ideas that we're going to talk about today. So hopefully we can get a good base, and after you do some homework problems, hopefully you can get a good understanding of this. And like I said, you're going to be using it again and again. And so it's something that you really want to make sure that you can kind of get down in order to do well in the course. Before I start on that, I just wanted to go over mastering chemistry, how the homework is graded. Sometimes it can be kind of foreign, I guess. So let me pull up the mastering chemistry. This is not exactly what you'll see. This is the instructor view, but oh, I gotta sign in again. Hold on. Sorry about this. Fast forward through this if you're not interested in me signing in. Okay, so if we go to the assignments, I'm just going to show you how the assignments are graded so you can kind of have an idea of what's going to happen when you're doing it. So as these become available, or actually I think I have them, they'll all be available starting Monday, June 22nd, the first day of class. So you should see all the different homeworks. There's 36 homework assignments for 36 different lectures. Again, there's one homework per lecture. And there's also just a bunch of practice problems for each chapter. So that's like if you're studying for the test or you just need more practice on a certain area, you can go back and look at those practice problems, and it'll give you new problems that you can try out just as like a study help for the test. Those aren't required. The only thing that's required is the assignments that are marked homework. These ones that are practice are just optional for you. But if we go into these different assignments, I can show you how they're graded. So let's see, grading settings. Okay. So the first thing to mention is that for every hour that you're late turning this in, you're going to lose 10% on the assignment. But I would never reduce that to more than 50%. So up to 5 hours late, right? If you turn it in like 4 hours late, you lose 40%. After 5 hours, it doesn't really matter. You're just going to lose 50%. And so this is like helpful if you miss the due date on an assignment, and it's like a week or two late, it's still worth it for you to go back and do it, not only for the practice, but you'll also get some credit for doing that assignment. So I did it to 50% just to give you guys a little more incentive to actually finish all the assignments. Even if you miss the due date, you'll still get some credit for it. But obviously, you start losing credit pretty quickly after the due date if you don't turn the homework in on time. As far as each question goes, you'll see two different types of questions, right? So you have your multiple choice questions. And so you lose a little bit of percentage if you get those wrong, but you won't lose all the points. So let's say it's like an A through D question and the answer is C and you choose A, you're going to lose partial credit for that question. But if you try again, and I'm trying to remember exactly what it is, it's 25%. So for example, if there's 4 choices and you chose the wrong one, let's say you chose A, then you can try the question again, and if you get it right, you actually get 75% for that question. So instead of just getting it wrong and losing all the credit, there's incentive to keep trying on the questions. For any other question type, so a lot of the questions will have you enter a number as an answer. Then you lose 5% for each incorrect answer. So let's say you do a word problem and you get it wrong the first time, if you try again and get it right, then you get 95% on that question. So that's kind of how the grading works, and hopefully that helps kind of just give you an idea. So even if you get a question wrong on the homework, keep trying and get it right, and you should be able to do pretty well on the homeworks. Even if you get a couple questions wrong the first time through, you're still going to do pretty well on the homework. So just wanted to show that real quick on how that's calculated. All right, so let's move into the PowerPoint presentation. Sorry, get this started here. All right, so we got the PowerPoint up. Okay, so like I said, this is lecture 2 on calculations. And just to start off, let's just kind of do a review from the last lecture. Anytime there's a quiz like this, you can go ahead and pause the video and work through the problem and try and solve it on your own. Okay, so now hopefully you've paused the video and tried to answer this. And we can go through this again. So if you remember from the last lecture, we talked about sig figs, or significant figures. If the number is written just as 500 like it is here, you have 1 sig fig, right? 5 is a non-zero, so that counts as a significant figure. And then these zeros are not significant because they're not sandwiched by 2 significant figures. They're also not followed by a decimal point. So if you look back to those 4 rules that I put in the last lecture, you can see what counts as a significant figure and what doesn't. And in this number, all that we have is the 5 here is significant, okay? So the 5 is significant, and then the zeros, oops, that's an X. The zeros are not significant, okay? And with this number here, we have our 5 being significant because it's a non-zero, okay? These 2 zeros are significant because they follow a significant figure, and they are followed by a decimal, which is one of those rules, okay, both significant. And then these 3 zeros are also significant because they follow a decimal and a significant figure, the 5 and these zeros. So that's 6 significant figures. Okay, and then this number here, right, these zeros are between a significant figure and a decimal, and so they also count as significant figures. So in this number right here, we have 3 sig figs. Okay. All right. So hopefully you can done the homework and have a better idea of what counts as a significant figure and not. And this kind of shows you that there's 3 ways, for example, to write 500. One shows 1 significant figure, one shows 6 significant figures, and one shows 3 significant figures. And then maybe just as a review, let's say you want to write 500 with 2 significant figures, okay? So go ahead and pause the video and maybe try and do this on your own. Write 500 to 2 sig figs, okay? Okay. So I'm going to show you how to do this, and if you forgot, this is a good chance to review. But what we need to do here is use scientific notation, right? So 500, if we do scientific notation, the way I like to do it, I put a decimal to help me know the exponents. And I need to move this decimal over 2 places in order to get just a number in the ones place. So 500 would be equal to 5.00 times 10 to the power of 2, right? The problem with this number is there's actually 3 significant figures here. So if I want to write 500 to 2 significant figures, I'm just going to write 5.0, which is equal to 5.00, but only has 2 significant figures. times 10 squared, okay? So this is a way to write 500 with two significant figures, okay? Two figs, okay. All right, so you can go ahead and try and, I mean, you could even say 4 sig figs, right? Let's say you want to write 500 to 4 sig figs. I'm just putting SF now. Okay, so we can write 500.0. Okay, so that's 500 written to 4 significant figures because all these zeros are now significant. So any number, you know, if you're struggling with this, just kind of do what I'm doing here. Say I want 4 sig figs or 5 sig figs or 7 sig figs, and you should be able to write any number to that amount of sig figs, either using scientific notation or adding a decimal point with more zeros at the end to make it significant. Okay. All right. Why do we care about this stuff, right? So let's look at a more real-world application, density. Okay, so density is defined as like the mass of a certain substance that occupies a given amount of volume. So certain materials will have different densities, right? Mass divided by volume. Okay, this is the, oops. This is the definition of density, okay? So a certain amount of mass per some unit of volume. So let's say we're doing the mass of this material, okay? I don't know exactly what material this is right here, but let's just call it like, I don't know, foam. This may be totally off, but I'm just gonna name it to give it a little more, a little visual here. So let's say you take 3 milliliters of foam, okay? So that's a volume amount of foam, and you put it on the scale, and the scale gives you 1.034 grams of foam, okay? So you know that 3 milliliters of foam weighs 1.034 grams. In order to get the density of foam, you do mass divided by volume. Okay, so if you went on your calculator right now and divided 1.034 divided by 3.0, your calculator spits out this number, okay? But it would be inaccurate to report the density as this number, because when you measured the mass, you only measured it to the thousandths place, right? You only had 4 digits of significance when you measured the mass. So you don't know what the rest of these digits are, right? Because your scale didn't tell you with that amount of accuracy how much it weighed. So if you go to report the density, all of a sudden, if you report this number, you're saying, I'm confident that I have this much accuracy in my measurement, which isn't the case because the tools you used to make your initial measurements weren't even this accurate in the first place, right? So what's happening if you do this is, you know, basically you're giving a density that's more accurate than you can really confidently state, okay? So there needs to be some rules that we follow when we do addition, subtraction, or multiplication and division with measurements, so that what we report is actually properly shows how confident we are with our answer, okay? So we want to know how many of these digits are actually significant, okay? So again, sig figs tell us where the error is in our calculation. So what we're going to talk about is how to figure out what is the error in our answer when we do math with significant figures. Okay. So if we look at the numbers that we measured before, right, the scale gave us 1.034 grams as the mass, and our volume was 3.0 milliliters of foam, okay? And again, remember the last digit in the measurement is always the estimated digit. So when we say 1.034 grams, what we really mean is it could be 1.034 grams, it could be 1.035 grams, it could be 1.033 grams, right? because this last one's just estimated. Same with the volume, okay? It's plus or minus 0.1 milliliter, maybe even 0.2 milliliters of inaccuracy, depending on the instrument that we're using to measure it. Okay, so let's just try adding and subtracting 0.1 mils to our volume and do the different calculations for density, okay? So let's say we take 1.035 grams divided by 2.9 mils, right? We're going to get this density. If we use different numbers, then we get this density. And again, a different set of numbers here. In this third row, we get a different density. So this just shows you that because you have this estimated digit, your density also contains some error when you do the calculation because your original measurements also contain some error. So if we look at this, the error is actually in the hundredths place, right? Every time we do the calculation, we get a different number in the hundredths place. We get a 5 or a 4 or a 3. Okay, so it's telling me that our density is accurate to this 0.3, right? Regardless of whatever combination we use for our measurements, we're going to get 0.3 something, okay? Which means that our answer for our density should have 2 sig figs. The first one is the 3, which we're confident about, and then the next one's the 5, which is our estimated digit. And this gives us 2 sig figs. Okay. So that was the case for a division problem. Okay, and division and multiplication we'll see follow the same rules. And we'll go over the rules in a second. But now let's look at an addition problem. Okay, and addition and subtraction are going to follow the same rules as well for significant figures. So where would the error be in this calculation, right? So if we add these two amounts of mass together, we're going to get some amount of mass as the answer, and we need to know how much error is contained in our answer. So again, this first measurement of mass, 9.787, the last digit is estimated, right? So this is our estimated digit. So draw a line here. So this is going to change. There's a little bit of error in that digit. And then our other measurement contains error in the last digit, as all measurements do. Okay. So if we try different combinations and add them all together, we see that our error is actually in the hundredths place. Okay, it might look a little weird here, but rounding this, you would see that the error is actually here in the hundredths place. Okay. So what that tells us is our significance goes out to the hundredths place, which is 3 different significant figures. Okay. So here we have 3 sig figs. And so what we learn from here, we'll go over the rules here right now, but going back to multiplication and division. So the rule that you follow, which is really the takeaway, I just explained the why, and hopefully it made sense. But if you pull anything away from this slide is what's really important, is that you pull away with these rules. Okay, so the rule for multiplication and division is that the number with the fewest number of sig figs sets the number of sig figs in the final answer. So if you're dividing these two numbers, this is our density example that we just went over. We have 4 sig figs in the numerator. 4 sig figs, okay? And then we have 2 sig figs in the denominator. So you look at the two numbers, and the one with the least number of sig figs sets the sig figs in your answer. So between 4 and 2, 2 is less, obviously. So that means our answer will be accurate to 2 sig figs, okay? So that's the rules with multiplication and division. You look at the numbers that are being either multiplied or divided, identify the number of sig figs, and then the number with the fewest number of sig figs sets the number of sig figs for the answer, okay? With addition and subtraction, the rule is a little bit different. We actually don't really look at number of sig figs. What you're going to do is you take the number with the fewest decimal places, sets the least significant decimal place in the final answer. So this can get a little confusing, but what you do is you look at your first measurement, and this is accurate to the tens, hundreds, thousands, 10,000th place, okay? And then this one here is to the 100th place. Okay, so I guess I should write this out. So the 10,000ths. Sorry, hard to write small in here. And then this one is significant to the 100th place. Okay. So you take the one with the fewest number of decimals, right? So there's 2 decimals in this one. There's 4 decimals in this one. So since this one has 2 decimals, okay, this one has 4 decimals. The one with the fewer number of decimals sets the decimal place for the answer. So again, 2 is less than 4, so that means our answer is going to have 2 decimal places. Okay. All right, awesome. Okay, so those are the rules, and that's pretty much what you need to pull away from this. So we'll go over a couple of examples to hopefully illustrate these rules and kind of walk through it. And there should be some practice problems on your homework as well to help with it. So let's look at solving this problem, okay? You can go ahead and pause the video, try and do this on your own first, and then we'll go through and look at the answer. All right, so let's try this out. So when you're doing multiple operations, right, first what we need to do is this subtraction problem that's in the numerator, okay? So let's look at this problem separately. Okay, so we take 125.65 minus 101, okay? So before we do the math, let's look at the number of decimal places. So the top number here is significant to 2 decimal places. 2 decimal places. The bottom number is significant to 0 decimal places, okay? And when we're doing addition and subtraction, the answer is significant to the number of decimal places of the least number here, right? So 0 is less than 2, so that means our answer is going to be significant to 0 decimal places, okay? So what you do is just go through this calculation on your calculator, okay? So if you did this on your calculator, you should get, run through real quick, 125.65 minus 101. Okay, that gives me 24.65, okay? So we know the answer needs to be significant to 0 decimal places, which means we need to round this number to a number with 0 decimals. So this is going to be rounded to 25, okay? All right, so we did that part first. Now we'll go ahead and do the rest of the problem. So if we rewrite that, we know we have 25 grams over 24.1234 grams, okay? So now since we're doing division, we look at the number of sig figs. So in the numerator, we have 2 sig figs. In the denominator, we have 7 sig figs, okay? So again, our answer is only going to be significant to 2 sig figs, right? Because it can only be significant to the number with the least number of sig figs here. So at this point, we don't even really need to do the calculation. If you look at your answers here, the only one that has 2 sig figs is E, okay? So we can just choose the answer as E. But if you did put this in your calculator, you're gonna do 25 divided by 24.12345. It's gonna give you an answer of 1.036, okay, grams. And then if you take that to, well, it's actually 1.036333601, whatever. But we know it can only be accurate to 2 sig figs. So if I round this number to 2 sig figs, I'm going to get 1.0 grams, okay, which is your answer here. All right, so sorry, the work that's actually done on the slide is kind of covered up by what I'm drawing, but that's so when you go through the PowerPoint later, it's not going to have my drawings on it, but it will have these calculations for you to look at, okay? So go through this, you got the answer E, okay? So those are these calculations that are typed in are there to help you when you're reviewing the PowerPoints afterwards. Okay. All right, let's look at another problem that we're going to solve. So an injured person loses 0.30 pints of blood. How many milliliters of blood would that be? Okay. So moving away from just talking about sig figs, now we're going to start talking about conversion factors as well. So most of the time when you're doing this, right, you want to know, oh, pints to milliliters, right? You go on Google and you say pints to milliliters, and then there's a nice little calculator, right? And you can just enter it in and you can solve it. But if you didn't have Google or some kind of conversion app or software, we want to know how we can do this the old-fashioned way, right? All right. So this is where we get into conversion factors. And these, let's see. I'm just gonna like star this right here, okay? Like I said before, if you can master using conversion factors to solve problems, you will do well in this course. This really is kind of the heart and soul of Chem 101. Some of you might be thinking like, why do I need to know how to do this, right? I have Google when I work as a nurse or a dietitian or whatever you're going into. You will have Google. You can do this on your phone, right? But don't think of this class as necessarily like the knowledge that's preparing you for your certain field. Chem 101 in my mind is really a class on problem solving. And so you might not find all these questions or things that we learn to be totally applicable in your field. But what is applicable is like looking at a problem and figuring out how to walk through it logically and solve it. And that's really what chemistry is all about for a lot of people. So anyway, my little soapbox there. If you're wondering why you have to take this class, it's not so that you can learn how to manually calculate between pints and milliliters of blood, right? There's other ways to do that that you'll probably use when you are working in the field or whatever. But what you will learn is how to solve problems, and I find that I have used that a lot more than the actual chemistry knowledge that I've gained in chemistry is using the problem solving skills that chemistry offers. So anyway, there you go. Okay, so we're gonna learn how to do this and really pay attention this first week. If you can nail this, then it's gonna help you so much throughout the class because we come back to this all the time. Okay, so conversion factors are really equalities. So we're gonna start with an equality and rewrite it as a fraction. So some examples. 1 meter is equal to 1,000 millimeters, okay? You can rewrite that as a fraction, right? Because anything over itself is equal to 1, okay? If you can't see this right now, basically what you need to do is You could use like some algebra, and you can figure it out. But anyway, the easiest way to think about it is just anything over itself is equal to 1, right? And so 1 meter, you can rewrite, 1 meter is equal to 1,000 millimeters. You could rewrite as 1 meter over 1,000 millimeters, right? Because these two are equal, then 1 meter over 1,000 millimeters is equal to 1. Maybe an easier way to see it is like if I wrote 3 equals 3, right? Everyone agrees with that, hopefully. Well, 1 is equal to 3 over 3, right? 3 over 3 is equal to 1. So anything that you can write as an equality, you can rewrite it as a fraction equal to 1, okay? And you can flip them as well. It doesn't really matter which one's on top or which one's on bottom, right? So you could put this 3 on top or the other 3 on bottom, whatever. The main thing to remember is that when you see an equality, you can rewrite it as a fraction equal to 1 with either one of these as the numerator and either one as the denominator. It's going to work. Another one is 1 pound is equal to 16 ounces, okay? Do 1 pound over 16 ounces equals 1, or 16 ounces over 1 pound is equal to 1. And same thing here with pounds to kilograms, okay? All right. So setting up the problem, we're going to walk through a few steps here. So kind of what I like to do is write the initial and the final units. And we'll walk through this in the context of problems coming up here in a sec, okay? So then you write a plan to convert the initial unit to the final unit, okay? So we need some kind of conversion factor that takes us from unit 2 to unit 1 or from unit 1 to unit 2, okay? And then you cross out using multiplication, right? You can cross out the units from the numerator and the adjacent denominator. And so you essentially go from unit 1 to unit 2, right? All right, this is kind of what I just talked about here. So this will be a lot easier to see in the context of a problem. So let's walk through it. Okay, so we have how many feet are in 5.5 miles? So again, we want to write the initial unit and the final unit. So our initial units here are miles, right? We are given 5.5 miles. That's what we're given. And the question says how many feet? So feet is going to be the final units that we want, okay? So we want our answer in feet, okay? So the next step in our process, right, is to come up with a plan to convert miles to feet, okay? So I'm gonna use a dot here. You can use an X. This is for the multiplication sign. In order to go from miles to feet, right, we need a fraction that contains miles in the denominator and feet in the numerator, okay? So then we look for an equality that we can use to create a conversion factor. Well, the question tells us that there are 5,280 feet in 1 mile, okay? So 5,280 feet is equal to 1 mile, right? And then we just learned that when something is equal to each other, you can rewrite it as a fraction, okay? So we can rewrite this as 5,280 feet. Oops. Over 1 mile. Or we could write it as 1 mile over 5,280 feet, okay? Well, if we look back at our setup that we used for the problem, we have feet over miles. That's what we want. So we're going to use this conversion factor here, or sorry, this fraction here. So if we put this into our problem, we have 5,280 feet for every 1 mile, okay? Should be mile, not miles, whatever. All right, so now we have our conversion factor in there. So now we can put back in our original miles that we started the problem with was 5.5 miles. So when we actually do this calculation, you can imagine if you want, you could put this over 1, right? Anything over 1 is itself. So sometimes it helps people to visualize this by drawing a fraction and writing this over 1 if you want. The 1 doesn't really do anything, but okay. So now what you can do is actually just run through this on your calculator. Our miles in the numerator is going to cancel the miles in the denominator. So the only units that we have left are feet. Okay, those are going to be present in the answer over here. So if I do 5.5 times 5,280, right? Let's see, 5.5 times 5,280. We get, sorry, I didn't leave enough room here, but 29,040 feet, okay? So again, these are just going to kind of walk through the plan here so that you can see it when you're reviewing the PowerPoint on your own. Okay. All right, so you can see this got 5,280 feet. Let me see if I can pull up an eraser here real quick, sorry. I don't see an eraser. Okay. Get rid of this writing for you. Okay, let's go back. Okay. So here's what you see when you just review the slides on your own. Okay, so the answer they got and what we got, they is in the PowerPoint. Anyways, 29,040 feet, okay? Now, if we think back to what we just talked about with significant figures, right? Now we have to factor these in while we're doing these conversions. So now we're going to kind of put it all together. So this question is, how many sig figs should our answer have, right? 1, 2, 3, 4, 5. We're not sure. So we're going to talk about this a little bit. The answer on this one is 2, okay? And we'll talk about this a little bit, I guess, to help you understand it. But you determine that your sig figs should be 2 in your answer. And so you actually rewrite this answer to a number that contains 2 significant figures. Okay. So determining how many significant figures is in your answer requires you to think about these 2 statements here. So if you're converting, if your equality is between units of the same system, then these we refer to as exact numbers, and sig figs aren't taken into account with those numbers. If you're converting between different systems, you use measured numbers, and these do count as significant figures with one exception. And then there's a chart to help you with that. So let's go over this. So let's say you're converting from feet to inches, right? Those are in the US imperial system, okay? So these are going to be exact numbers, okay? If you're converted between yards and feet, same. Miles and feet, like we just did, same system. So they're considered exact numbers. If you're within the metric system, they're considered exact numbers, and you don't have to worry about sig figs on this one. If you're converted between metric and US, that's where you're going to have to think about the number of significant figures. The only exception, like I mentioned, is when you convert between centimeters and inches. This is actually defined as an exact conversion, and so you don't think about it in this case. So that's the one exception. Let's go back though to this problem here, okay? So the question I posed was, how many sig figs should our answer have? Okay, so the actual calculation is right here. Go back. Okay, so this is our calculation, right? And our answer was 29,040 feet, right? Okay, so we're doing a multiplication problem here. So our answer can only have as many sig figs as the number with the least number of sig figs that you're multiplying. So 5.5 miles is a measured value, and that contains 2 sig figs, okay? 5,280 feet per 1 mile. This is an exact conversion, right? Because feet and mile are both in the US imperial system, okay? So this is an exact number, so you can just put exact. So in this case, you don't have to decide which one has the least number of sig figs, because there's really only one measured value that has sig figs. And so our answer only has 2 sig figs, because 5.5 miles is 2 sig figs. And this number you can almost think of as an infinite number of sig figs if you want, but we just call it exact, right? And so you don't take that into account when you're determining how many sig figs your answer will have, okay? All right. So hopefully you'll see some practice with that in your homework. Or if you have any questions, email me and we can go over it in office hours and talk about that a little bit more as well. All right. Sometimes as we get into the course a little more, you're going to see more confusing conversions that require to use multiple conversion factors, okay? So sometimes it's not as straightforward as converting feet to miles, all right? But it's really the same process. You'll just have to have additional conversion factors, right? So additional conversion factors are placed in the setup to cancel each preceding unit. We'll see how this goes. So let's say you need to go from unit 1 to unit 3, and you're going to have to pass through a unit 2 in order to get there. Okay, so you're going to have to convert unit 1 to unit 2 using this conversion. And then you'll convert unit 2 to unit 3 using another conversion, which gives you the answer unit 3. Okay, so let's look at this example that we talked about before. So an injured person loses 0.30 pints of blood. How many milliliters of blood would that be? Okay, so on a test, you'll be given conversion factors for conversions that you're not really, that are kind of weird and out there, right? So for example, quarts to liters, I don't expect anybody to memorize that. Quarts to pints, I don't really expect you to memorize that either. The only things I think you should know off the top of your head are when you're converting between like liters and milliliters, right? Or liters, or sorry, like grams and kilograms, okay? So learning the prefixes before each number is gonna help with that. But even those, right, these you'll kind of just get a lot of experience with, and it'll come hopefully pretty naturally as you move through the course. Okay, but say this is all we're given, right? We don't have anything. Let's say if we look at our process for setting things up like we've done before, our initial units are pints, okay? And our final unit we want is milliliters. Well, it'd be nice if we had a conversion factor, right, that would take us from pints to milliliters, okay? But we're not given a conversion. All we have is pints to quarts, quarts to liters, liters to milliliters, right? We don't have a pints to milliliters conversion factor, so this approach doesn't work. So again, let's write out our initial units. So those are pints, okay? And our final units are going to be milliliters, okay? So let's look at what we have. We have something that takes us from pints to quarts, and that's the only conversion factor that we have that includes pints. Okay, so we're going to have to, let's see. Okay, I just have to write over this. Sorry, ignore that line. So we'll go from pints to quarts using this conversion factor right here, okay? And then we can go from quarts to liters using this conversion factor here. Okay, so that'll take us to liters. And then we actually have a conversion factor that takes us from liters to milliliters. So we can make this final jump using this conversion factor, okay? So let's write this out. So we have pints, okay? And then we have this conversion factor that takes us from pints to quarts, okay? So we'll set this up with 2 pints on the bottom to 1 quart, okay? And then we're going to use our second conversion factor, which takes us from quarts to liters. So we can say 1.057 quarts. That's a G. That should be a Q. Quarts to 1 liter. Okay. And then we have this final conversion factor, which takes us from liters to milliliters. Okay. So hopefully you can see I'm using all these 3 conversion factors to finally get us to milliliters. Okay. All right. So, all right. So now let's work through this. So we start with 0.30 pints. Okay. And then our pints are actually going to cancel out. Our quarts cancel out. Our liters cancel out. And we're left with milliliters as our final unit, right, that we see over here. So now we can put this into our calculator. And I think the easiest way to do this is to multiply all the numerators together and divide it by all the denominators multiplied together. So that's usually the easiest way to put it in your calculator. So in your calculator, what you would actually enter is 0.3 times 1,000. Okay. All right. So that would give you what, 300? Okay. And then you would divide that by 2 times 1.057, which would be 2.112, I believe. Let me just double check that. Times 114. Sorry, I messed that up. 4 here. Okay. All right. So then it's a little easier. So I should write this out. 2 times 1.057 equals 2.114. Sorry about that. So then once you have these two numbers, you can go back into your calculator and do 300 divided by 2.114. Okay. And the answer there is sorry, I'm still getting used to this pen, 141.911. Sorry, that's ugly. Let me do it again. 141.911,069. Okay, so that's the number that you come up with your calculator. Now there's one last step before we can report the final answer, right? We need to know how many significant figures we can report in our answer. So let's go through these numbers. 0.30, okay? That's 2 significant figures. Okay. Quarts to pints, quart and pint are in the same system. They're both in the US system. So that's an exact conversion. Okay. Liters to quarts, that is between the US system and the metric system. So since this is across systems, we actually look at sig figs here. Okay, so we have 1 liter, and we're going to say this 1 is exact, right? Because in 1 liter, we're going to estimate that there are 1.057 quarts. So between these two numbers, the 1 is actually exact, and the estimated number is this bottom number, and it contains 4 sig figs. Okay. All right. And then this last conversion is between milliliters and liters. And that's both, those units are both within the metric system. So this is an exact exact conversion. So now we have a 2 sig fig, an exact, a 4 sig fig, and an exact, right? And so the least of all these is the 2 significant figures, which means our answer can only have 2 sig figs. So our answer, if we round 141.911069, right? Sorry, I need a little more space for this. Our answer is going to be 140 milliliters. Okay, so that has 2 sig figs. The reason I rounded this, right? If you do round this number to the ones place, you have 142, but 142 has 3 significant figures, so you need to actually round it one place further to 140 milliliters. So your answer is only reported in 2 significant figures. Okay. Oops. Sorry. All right, I'm going to back up to kind of see if I can erase all that and then come back and kind of walk through the PowerPoint as it's written out. So this would be the plan, right, that we went through to get from pints all the way to milliliters. And then we can write it out just like we did with the pen. This is obviously a lot more clear, which is nice. But I like to show you with the pen just to walk through it, to kind of show you the process that I go through when I solve these problems. So 141.911 milliliters, right? And again, these are the 2 numbers that we're going to look at to determine how many significant figures are there, because this conversion and this one are exact. And this one, we say is an exact number because we're just estimating the number of quarts in 1 liter. So 1.057 is estimated or measured, you could say, and then the 0.30 is estimated as well. So our answer needs to be within 2 significant figures to give you 140 milliliters in your answer. Okay. So the last little topic we're going to talk about is density. Okay, so density is a property that we're going to talk about throughout the course. But every pure substance, like it says here, has a certain density related to it. Okay, and density, like we talked about, is mass over volume. Sometimes you'll see it written with this Greek symbol, M over V, but just worry about, the principle here is mass over volumes equals density. And so you can actually use mass over volume as a conversion factor, and you can use it to convert. So far, all we've done is converted between volume units, right? So you went from pints of blood to milliliters. And you went through a number of conversions to get there, but essentially pint and milliliters are 2 units that measure volume. So let's say you want to convert from volume of something to the mass of something. Then you'll need density because it actually converts between mass and volume, right? You can use this fraction as a conversion factor. So, sorry, this mentions the exploratory lab, which we're not doing because the class is online, so you won't have to worry about that. Okay, density generally is written as grams per milliliter, okay? And then also something to note is that sometimes you'll see milliliters, sometimes you'll see centimeters cubed, okay? They're interchangeable because 1 milliliter is equal to 1 centimeter cubed, okay? So you can write them interchangeably, sometimes you'll see them used interchangeably. Okay, so again, this looks like a conversion factor, right? There's a fraction that we can use. Okay, so let's look at this problem. Lead has a density of 11.3 grams per milliliter. So then we want to answer the question, what is the volume of 2 kilograms of lead? So if you have 2 kilograms, how much space does that take up? Okay. So our initial unit here is kilograms, and we want to get over to volume in milliliters. Okay. So in order to use the conversion factor here, we need our units to be in grams. So we convert kilograms to grams using this conversion factor, because 1,000 grams is equal to 1 kilogram, okay? So that's what you see here. 1,000 can also be written as 10 to the third, okay? 10 to the third grams equals 1 kilogram, okay? So that's written as conversion factor. And then we use the density, which is 1.3 grams per milliliter. And again, since it's a conversion factor here, we can flip it around, right? So this 11.3 could either be on the top or the bottom. So here we have 11.3 grams on the bottom with milliliters on top. And the reason we do that is because we want the grams to be on opposite sides so that they can cancel out, okay? So, sorry, before we get there, kilograms is going to cancel, grams is going to cancel, and we're left with milliliters in our answer, okay? So again, this is kind of what you would want to put into your calculator, do the calculation, and you get this answer. So now we got to go back and look at sig figs before we can report our final answer, okay? So 2.0 kilograms, it's a measured value, so that will have 2 significant figures, okay? This conversion between grams and kilograms is in the same metric system, so we're not gonna, so that's an exact, okay, exact conversion. And then the density is a measured property. So the 11.3 is 3 sig figs, okay? So our answer can only be to the least amount of sig figs as the numbers we're multiplying or dividing. So our answer is going to be accurate to within 2 sig figs. So if you round this number, right, if you round it to the ones place, which is commonly what people think about, right, you have 177. But we actually need to round it to 2 sig figs. So now if you round 177 to 2 sig figs, that actually gives you 180, right? So 180 milliliters is going to be what you would report as the answer for this problem. Okay, and then similarly, we could go from volume to mass, right? So in this case, we'll start with liters, and then we need to get liters into milliliters in order to use density as a conversion factor because the units in density are milliliters. Then we can pop in the density and solve for the mass. So the liters cancel out, the milliliters cancel out, and we're left with grams, okay? So again, this is what you would put into your calculator, all divided by 1 because that's what's here. So you don't really have to divide it by 1 in your calculator because anything divided by 1 is itself. Okay, and the answer your calculator gives you is 11,300. And then again, 1.0 liters, that's 2 sig figs, okay? This is an exact conversion, and then we have 3 sig figs on this number, okay? So that means your answer needs to be reported to 2 significant figures of accuracy, so you'd round this number to 11,000 grams. And then you can convert to kilograms at the end. This isn't really required unless the question asks for it, okay? All right. So do this little problem here, try it on your own and see how you do. Go ahead and pause it. All right, let's go ahead and work through this problem now. So the density of octane, right, which is comprises a large part of gasoline, is 0.702 grams per milliliter, okay? So this is our density, and we can write that as a conversion factor. So what is the mass in kilograms of 875 milliliters of octane? So our initial unit is going to be milliliters. We have 875 milliliters of octane. Okay, and then we need to convert the milliliters into a mass, so grams, right? And then we need to convert it into kilograms at the end, just because that's what the question's asking us to do. So in order to convert from milliliters into grams, we know we have this density here, right? And we know that it converts those two because the units have a grams over milliliters. So we'll write this as 0.702 0.702 grams over milliliters. And you could put a 1 here if you want. You don't need to, but sometimes it helps people see it better. So that means that these milliliters would cancel out, right? And then our answer would be in grams, but we want our answer to be in kilograms. So we know that 1,000 grams is equal to 1 kilogram. And again, this is just knowing those metric prefixes that, that you need to learn. Okay, so then we can write this as an equality, and we'll put grams on the bottom. The reason we want it on the bottom is because we want the grams to cancel out, right? So the grams over here is on the top, so this one needs to be on the bottom so that it can cancel out. And then we'll put kilograms on top. So grams cancels out now, and we're left with kilograms for our final unit, okay? All right. So if you put this in the calculator, you would do 875 times 0.702 times 1. Okay, so that would give you 614.25. And then you divide that by 1,000. It gives you 0.61425. Okay, that's what the calculator gives you. And then the final step is to make sure this is in the correct number of significant figures. So 875 milliliters, that's a measured value. So we have 3 sig figs. Density, right? We're going to look at the number of sig figs in the grams, right? Because per 1 unit of milliliter, we're going to estimate that there's 0.702 grams. So that also contains 3 significant figures. And then this last conversion is exact because you're converting between 2 metric units, so within the same system. So if we estimate this number to 3 significant figures, we should get 0.614 kilograms, okay? So it looks like your answer would be A. All right, let me come back here and kind of walk through it with the, oh, sorry, yeah. There you go. That's the process right there. All right, so moving on. Okay, so just as this last idea, the reason density is interesting or useful is we can use it to tell if something's going to sink or float, right? So normally we have demos in class, and I can kind of show some of these things, but unfortunately might just be limited to pictures and maybe some YouTube videos for the online version. So if we look at the densities of these different things, the density of water, right, which is listed here, is 1 gram per milliliter. Anything less than that has a smaller density than water, and it's actually going to float. Okay, so ice actually is less dense. Ice is water just frozen, right? But when it freezes, it becomes less dense. And so ice will generally sit towards the top of the water. A cork is even less dense, and that's going to float on top of the water. And then metals are generally denser than water, right? So they're going to end up sinking to the bottom of the cup because they're more dense. So yeah, you can kind of use that test, right, to tell if something's more or less dense than water. Put it in water. If it floats, it's less dense. If it sinks, then it's more dense than water. Okay, so for the last slide here, we're going to talk about just some more problem solving. Okay, so sometimes you'll see a problem like this where initially it might look confusing, but this is where units are really helpful. Okay, so let's say we have an unknown metal and we want to know what it is, and all we have is a table of densities. Okay, so we have a table of densities that shows the density for titanium, zinc, cobalt, and lead. So in order to determine what the metal is, first thing you do is you put it on the scale, and the scale says that that sample of metal is equal to 64.4 grams. Okay, that's what the scale reads. And then let's say you have a beaker of water, okay? And in this beaker there's 10 milliliters, okay? 10.0 milliliters is what you can measure. And then after you put the metal chunk in there, okay, it reads 15.7 milliliters. So calculate the density and compare. So if we remember, density equals mass over volume, okay? We know what the mass is because the scale just gave it to us, and that's 64.4 grams, okay? So the volume is going to be whatever the final volume of water is after you put the metal, sample of metal in the beaker, minus the initial amount of water, right? So this is kind of known as like the water displacement method. But if you put the object in the water level rises the amount of volume that that sample took up, okay? So if you take 15.7 and you subtract 10.0 milliliters, right? That's going to give you the volume of your metal sample. So go ahead, maybe from at this point, try and pause the video and solve this problem, okay? All right, so let's go ahead and walk through this. So first, all we need to really do is get the volume of the metal sample, and we'll pop it here on the bottom and do this calculation, and we have our answer. So 15.7 minus 10.0 milliliters. If you put this in your calculator, you're going to get 5.7 milliliters, right? So we'll put that up into the denominator here, 5.7 milliliters, okay? All right. So now if we do this calculation on the calculator, we'll do 64.4 divided by 5.7. Okay, our answer is going to be 11.298, and it kind of continues, okay? If we look at the two numbers that we divided, the numerator has 3 sig figs and the denominator has 2 sig figs, so our answer should be accurate to 2 significant figures. If we round this number to 2 significant figures, we would get 11 grams per milliliter as our units. And that is D, lead. So lead would be our answer, okay? I think that's the end of the slide there. Okay, so hopefully that made some good sense. Again, spend some time practicing this. You can rewatch the lecture or spend some time on doing practice problems, and make sure you do the homework. It really gets this idea of significant figures and conversions down, because it's something that we'll see in practice again throughout the semester. So again, if you have any questions, you could email me, come to office hours, or even if you want to utilize like comments on YouTube, you could post a comment and say like, at this point it didn't really make sense, and I'll either I can go over it in office hours, or just reply to your comment on YouTube and see if I can clarify things. So, all right, have a good one.